All right, now that you've gotten a decent introduction to the periodic table, let's look at some of the other pieces of information that we can get from the table. In other words, how do we classify those elements? Yeah, they have symbols and names, but is there anything else about them that makes them special? Here you have your regular old periodic table, and if you've ever looked at it, there's this weird bold staircase right in the middle. It kind of looks like a set of stairs, and it's there for a reason. It's kind of like the Great Wall of China. It divides it into two halves. The majority of the elements on the periodic table, these are going to be metals. All of these elements here. That guy's a metal. All metals. They're lustrous, they're shiny, they're good conductors, all properties of metals. On the other side of this staircase, all of these guys, these are non-metals. Fancy, just the opposite name. So you've got your metals and your nonmetals. Notice how we include hydrogen over here. Hydrogen is in group 1 because it has that one valence electron, so that sets him over there. But he is pulled up top because he is a nonmetal. And there's also something weird with his electrons that we'll talk about later. Then we have to talk about, well, why? I kind of avoided, if you notice, with the elements on the staircase. These are called metalloids, and they're essentially a blend of both metals and nonmetals, and there are 7 of them. Boron, silicon, germanium, arsenic, antimony, tellurium, and astatine. Aluminum and polonium, although they're sitting there, just simply don't have the properties of a metalloid, so they're qualified as obviously metals. Metalloids are hybrids. They do a little bit of both. So if we look some of the properties of metals, you're probably very familiar with. If you look at excellent conductors, metals, we say that they're malleable, meaning we can hammer them into a sheet like aluminum foil. And we know that they're shiny. And we look at nonmetals, they're bad conductors. In fact, if you think about what the opposite of a conductor is, it's an insulator. So rather than letting heat pass through you, you actually keep it inside. They're also brittle. Think about like a marble statue. You hit it with a hammer, you don't smush his face. You break his face. And finally, they're dull. Graphite, like your pencil, it's not very shiny. It's a little bit more dull. At least not as shiny like a silver would be. And then finally, you have your metalloids. Most famous one is going to be silicon. They're called semiconductors, and they kind of play both sides of the fence. The next way we can look at elements is simply who's a solid, who's a liquid, who's a gas. Probably the most basic way of looking at them of all. And if you look, you'll see that the majority of the elements are solids. Some of them are softer than other. Sodium actually is so soft you could cut it with a knife. We obviously know we can't cut lead with a knife. You do have 2 liquids. You have mercury and bromine. Mercury is that nice, shiny, metallic-y liquid. It used to be in thermometers. And bromine is your non-metallic liquid. So it's really easy to tell the difference between them because mercury is super shiny. And then finally, you have 10 gases. The noble gases, of course, and then hydrogen, nitrogen, oxygen, fluorine, and chlorine. And the reasons for that is something we'll discuss a little bit later. And then last but not least, how do we find these things in nature? Because we know that we have helium tanks and we just blow up helium. So obviously helium, I can just go out and buy some helium. But I can't just go out and like kick around and look for some sodium. And there's a reason for that. Number 1, sodium is in group 1. So he's so reactive that he is never found alone in nature. Because they're so reactive. They're looking for a partner. It's kind of like those people that like can't live without a boyfriend or a girlfriend or like can't live without their best friend. Those are most of the elements. They're always tied up in some compound. Even when we go looking for gold, we don't just find gold, or iron, I should say, is a better example. We have to find iron ore. And then we have to pull the pure iron out of that ore or that mixture. So most elements are actually found in compounds, but there are some that we can find pure, and most of the time they are nonmetals. And we've talked about the diatomic molecules. These are 7, they spell out Brinkelhoff, 7 nonmetals, and they essentially go nowhere alone. They're Twinkies or the twins. And we'll talk about why when we get to bonding, but they're just super reactive that if I don't have anybody else to hang out with, I'm going to hang out with you. So bromine and bromine go off in the world together. And finally, we have monoatomic molecules. And one thing I'm going to ask you to think about is all these other people have partners. All these other people hang out with other elements. Why are the noble gases the only ones that actually hang out all alone? Monoatomic, just one atom, one little hydrogen atom can literally exist on its own. And I want you to think about why. And then the last, and this is kind of interesting, the last little thing is something called allotropes. Normally they occur with nonmetals, and 2 of the most famous examples are the allotropes of oxygen and the allotropes of carbon. And before you start writing, I just want you to look at the differences between O2 and O3. And you should notice that O2 is linear. 2 atoms just set up side by side, while O3 has more of a bent shape and it has 3 instead of 2. Well, that right there is the definition of an allotrope. They have different molecular structures. And because of that, they give us different properties, similarly to how proteins. Mr. van der Kroek talked to you about proteins and how the shape of those proteins dictates their function. It's kind of the same here. This linear molecule, we breathe in every day. If we didn't have it, we would die. This bent molecule, kind of a boomerang shape, it would be poison to us if we breathed it in. We know that it's up in the outer places of our atmosphere, but we don't breathe it in. It would be toxic. And then we have diamond and graphite, which if you don't know, these are both allotropes of our good old friend carbon. And carbon can just hang out as carbon, but it also exists as diamonds, graphite, even coal. And if you look at these graphite atoms, it's kind of a hexagonal ring, and they're attached in sheets. And if I look at one carbon in the middle, he has 3 other bonds. Every carbon has 3 bonds to it. And what happens is these are layers, and then they attach themselves, that's a really bad dotted line, on top with these other forces of attraction. And we know that graphite, these forces of attraction are really easy to break. I apply a little pressure to my pencil and I break them in half, and this is what ends up on my paper. Diamonds, on the other hand, if you look at their structure, pick one atom. It's got 4 bonds around it. And it sounds crazy, but just that addition of that one bond in every possible direction makes diamonds much, much stronger. And that's exactly why diamonds are some of the strongest materials on Earth. And if you look at the pictures again, clearly they have different structures. Graphite are these layers, while a diamond is a nice, it's almost a repetitive network of these bonds. And that therefore gives them different properties. One last thing about the periodic table before we start looking at some questions as to how this would be. Why is that doing that? These are some of the most important groups that you have to know. And if you look at them, the transition metals, again, like I mentioned in another video, they're kind of lumped together because they behave very similarly. But if you look, you have your alkali metals in group 1. Your group 2 metals are called your alkali earth metals. This is kind of hokey. They're not given fancy names, unfortunately. Your group 17 are called your halogens. And group 18, this says inert. We like to just call them noble gases. These down here, you do not need to know by name. These are rare, or most of them are radioactive, so they're very unstable and they don't exist for very long. So we're going to talk about all of these properties in class. It would make no sense to take up time doing this in a video, so we'll just hold on to this for next time in class. Same thing here. This actually is going to be a really important chart for us when we get to bonding. Finally, let's just talk about what you should have been able to gather from the video. Pick out who are the metals, nonmetals, and metalloids. Who are my solids, liquids, and gases? What does it mean to be monoatomic or diatomic or even allotropic? And then finally, can you name the 5 major groups of elements? So let's take a quick look at some questions. Identify the following elements as being metals, nonmetals, metalloids, or noble gases. Well, this just makes you have to take out your periodic table. So I want you to pause the video if you don't have it out already and just practice. See if you can find out which ones these are. All right, check what you got. Potassium and rubidium are to the left of the staircase, so they are metals. Antimony and silicon are one of the 7 that sit on the stairs, so those are metalloids. Nitrogen and bromine are to the right of the staircase, making them nonmetals. Neon is simply a noble gas, and francium is a metal. All right, next one. Which of the following elements will form monoatomic molecules? Monoatomic means that they are allowed to exist as one because they don't need a friend. Who doesn't need friends? The people with 8 electrons in their outermost shell. Those are going to be your noble gases. Which of the following elements is a nonmetallic gas? Well, here's how I do these. Non-metal means zinc is out and mercury is out because those are metals. Then we go down to bromine and chlorine. There's only 2 liquids on the periodic table, and you got to know them by name. Bromine and mercury. We already eliminated mercury because he's not non-metallic. That brings us to bromine. Oh my God, I'm reading the question wrong. How many of you can relate to that? A gas, this is a liquid, so it's chlorine is the gas. Which of the following elements is a metallic liquid? Let's take the same approach. Metallic, bromine's not metallic, chlorine's not metallic. And again, you've got to know these 2 by name. Mercury is your metallic liquid. And then finally, which of the following elements form diatomic molecules? These are your Brinkelhoffs. Spell it out. BRINCLHOF. Those are your elements, and nitrogen is the only one. So here's some more practice you can do to kind of summarize the 2 first videos that you have. Again, as always, take down any questions you have if I lost you at any point, and make sure to ask them in class and through your summary form. Thanks for watching.